Okay, the compressor. Compressor is a very interesting part in terms of flow control because it has some specific characteristics, the compressor. You want to increase pressure ratio or pressure by applying a pressure ratio, put energy into the flow, and then you've got the risk of a flow instability because the back end pressure is higher than the front pressure. You might have backflows and a detaching flow, especially on the airfoils. You can imagine that turning a flow in a direction where the pressure is higher is very difficult to do that. So, just briefly explaining the topic here on the compressor map. We've got pressure ratio over flow and an operating line together with the operating point here. When you move this operating point towards higher pressure ratio, there's a stability limit, which is called surge line or stability line. Once you cross that limit, you will see that sometimes. Yeah, you can have complete backflow. The flames will come out of your fan and also taking the oscillatory part going through the turbine. And yeah, maybe you will even lose your engine here.
Or at least some of the blades are contained in the backflow.
The important part, at least you will lose your thrust. And especially during takeoff, that's a really undesirable case. So we've got to avoid that. And therefore we've got a number which is called surge margin, which gives you the distance between the operating point and the stability limit. So this is this distance. The problem we have in real life is that neither the surge line nor the operating point are fixed, but they move. The surge line can move downwards, the operating point can move upwards. So there may be cases where operating point crosses the stability limit. For example, during an acceleration, which you can see in this green path, there can be very critical circumstances. So today the status is that we have to keep safety margins to enable the stable operation of the engine. And what we want to do is that we want to do that actively. So actively increasing the operating range of the compressor and also make it more tolerant against the disturbances. And once we have that technology which can actively increase the operating range, we can change the design of the compressor. And this will give us an efficiency benefit and a weight benefit. So this is very interesting for new engine designs. Currently we have got, as I said before, variable guide reins, which is an active technology, as well as bleed air already, but all these are scheduled and don't react on anything which goes on in the engine. And we've got a passive method which is called casing treatment, which are kind of grooves in the casing with increase the pressure ratio of the surge limit.
Modify the flow structure about the blade basically.
So now looking at active surge control. To enhance the operating range of the compressor, you have got the possibility that instabilities go along with instability precursors, which are pressure signatures which occur before the actual instability event. And you can sense these pressure fluctuations. You need very high frequency here. You have got early detection before the event starts. And you have to consider the spatial correlation of these disturbances, so spatially about the circumference. You also can have model-based instability predictions. So you would have an onboard model then, which currently periodically calculates your current and future surge margin. and then predict what the event which is coming up. From the actuation side, we've got three major actuations which can cope with a problem. We've got quick guidable movement, but it turned out here that guide vanes are mechanically complex and not the quick movement is not so easy, so they can't move quick just because of the masses involved. Another possibility is tip injection, which means blowing a jet into the tip gap region. And I've got this example drawn here with tip injection. So baseline basic principle is the detection of an instability before the big instability occurs. Then you can activate your jet, blow it into the tip gap region, and what happens is that entropy and flows, entropy is very much reduced, flow vortices are reduced, and this gives you a more stable flow at the stability limit. And now you can enhance your operating range by just blowing into this tip gap region, as shown here in the green range, and you will obtain a range that was formerly not present. So you can operate the compressor simply with a higher pressure ratio. Another feature is tip clearance control, which I will show later, which is also a mean for enhancing surge margin. This is an example of active stability control with tip ejection, which was done at the University of Armed Forces in Munich. They took a Lazard engine, took air out of the HPC, or took simply shop air, which you do in the laboratory, blew it into the front phase, into the tip gap region of the low pressure compressor, and therefore stabilized the flow. And they could also sense the pressure signatures before the stability event. These Q-lights here, these which are very high frequency pressure transducers. They have got several positions around the circumference. They analyze the signal, and then if an upcoming instability event was recognized, they turned on their injection, and by doing that they showed that the engine, the overall engine, could be operated in a region which was formerly not possible. So moving on a bit to flow control, which is a larger word for the same thing, in fact. So you also see tip injection here as a part of this flow control. Case impediment is a kind of passive flow control, and also clearance control. And you always try to manipulate the flow in the tip gap region here of the plate. During off design, you can see that there's a strong secondary flow field here in this tip gap region, so you're trying to improve that. But there's also a complete flow field over the airfoil, and there are other regions which are important if you want to enhance surge margin, like the hub, for example, where you've got horseshoe vortices, as we call it, so rolling vortices from the hub to the trailing edge. And there also, you can also have separations here on the trailing edge. For example, where you can apply microjets and manipulate the separations in this region. You also can have variable airfoils to provide changing shapes of the airfoil geometry to improve the flow on the airfoil itself. And I would like to show you an example from NASA, a simulation example, in fact. Here they've got a very simple channel, straight channel, flat plate, if you want to, with a bump in it. And over this bump there's a separation occurring. If you are doing nothing, you have a separation over this bump here. When you begin to suck away the separation bubble, you of course will have a very small separation. So because it simply sucked away with all this low momentum fluid. What you can do now is you can have oscillating jet, so sucking and blowing it's, at a specific frequency, which has been done here just by moving this wall. So there's a jet coming out of that, and periodically you suck. So that's the example here, and it was modeled with CFD, with computer fluid dynamics, computational fluid dynamics, and it turned out that normal turbulence models fail to predict these phenomena, which is a very important point for active control. Here, you had to apply specially adequate models like LES, large eddy simulation, and runs, Reynolds average, Navier-Stokes, to model these turbulent structures, which are shown here, like strike vortices, a very, very turbulent, very complex flow structure. The point why I'm showing that here is that once you are able to predict this flow, really to simulate, you're also able to predict what your active control does. And you're able to predict where you have got to manipulate the flow to improve the overall situation. And this is shown here. So they optimized the jet coming out of this pump. And the colleagues here showed that by having only a duty cycle of 10%, so having only 10% of actuation, it was possible to get almost the same effect. So they had a small peak of velocity coming out of the small holes. Before they had this big actuation, now only small pulse jets, and therefore you can see here in the pressure coefficients over the length of the duct, they got a complete attachment of this flow by only actuating 10%. So the point for active control is that you can eventually manipulate the flow by only a very small actuation. So this small actuation can cause a very large effect if you do it correctly. So in order to do it correctly, you need to understand the physical process. It's very important here, and therefore you require exact simulation methods. Okay, moving on to some other examples of flow control. Here, for example, there's an aspirated fan stage. This aspiration is done by holes in the hub, in the casing, and on the airfoil, where you suck away low momentum fluid. And if you do that on the right positions, you are able to get a very high pressure ratio with only one fan stage, and you won't have any separations in zones where you would have separations without active